Hello class, this is Miss Riggins coming to you with another video regarding similar triangles, and we're going to actually be combining that topic with right triangles and combining with another topic you know something about, which are altitudes. So let's take a look at a regular right triangle, and as you can see we have a regular right triangle, and we know it's a right triangle because it has a right angle. And this triangle ABC has two legs and it has a hypotenuse, okay? So what we're going to do is we're going to draw an altitude from the right angle. For those of you who don't remember what an altitude is, an altitude is a line segment that starts from the vertex of a triangle and is perpendicular to the line containing the opposite side of a triangle. So here is our altitude. As you can see, it starts from the right angle and it intersects the third side at a right angle. And we're going to call this altitude, the length of the altitude, as x. Okay? When we produce that altitude, what happens is that the triangle, the main right triangle, is broken up into two smaller right triangles. So let's take a look at the first right triangle. We're going to call that triangle ACD. And as you can see, the right angle is at angle D. And these are the angle measurements for the other angles. And the other right triangle, the right of the right triangle, is this triangle. We call that triangle CBD. The right angle is at D, and here are the angle measurements, as you can see. So what do you notice about the relationship between these two triangles? If you base off their corresponding angles, you will see that the angle measurements are the same. So we can say that the two triangles have to be similar. But not only are these two triangles similar to one another, if I show you the angle measurements from the main triangle that we start off with, angle ABC, we see that their angle measurements are also correspondingly congruent to the corresponding angles in each of the other two triangles. So we have here two similarity statements. That triangle ACD is similar to triangle ABC, which is the main triangle, but ACD is also similar to triangle CBD, which means that all three triangles are similar to one another. So what are we going to do with that? Well, because we know that all three triangles are similar, we can write some proportionality statements. As you can see, we have here, since we know these two triangles are similar, that triangle CBD is similar to triangle ACD, then the corresponding side lengths are proportional, which means we have this proportionality statement. So let's take a look at what we can do with this proportionality statement. From this proportionality statement, I take the last two pieces, and I see that side BD over CD is equal to CD over AD. Well, for those of you who may or may not recognize CD over CD as being the means or the extremes, there is a relationship that we've seen before where you have the same variable or value in the denominator of one ratio as is in the numerator of the other ratio. If you guys remember what that is, it sounds very familiar to the geometric mean. So that leads us to the geometric mean altitude theorem. And the geometric mean altitude theorem says if I replace what BD represents, and as you can see here, BD represents a part of the hypotenuse, I end up with, we end up with this relationship, which looks very similar or familiar from the geometric mean. But what does BD represent in this situation? What does AD represent in that situation? Well, BD and HD both represent pieces of the hypotenuse. So if we take a look here, this hypotenuse has been broken up into two pieces, H1 and H2. So if I take a look at this relationship, then that means the geometric mean altitude theorem looks something like this, where H2 represents the piece of the hypotenuse and H1 represents the other piece of the hypotenuse, which means that the geometric mean of the pieces of the hypotenuse is equal to the length of the altitude. And so this is very important, and we're going to put it up here because you're going to need to save this, because this is going to become very useful in the classwork for the next period. So if you haven't already, please write that down in your notes. So let's go back to our notes. since we already shown that if we have an altitude drawn to the hypotenuse of a right triangle, then the two triangles formed are, what's the relationship between them one another? If you said similar, you're absolutely correct. So that means these triangles are all similar to one another. So from that leads our first theorem that we just talked about, which is a geometric mean altitude theorem. And the altitude being the length of the altitude from the right angle. So in a right triangle, the altitude from the right angle to the hypotenuse divides the hypotenuse into two segments. I called it H1 and H2. And in that case, the length of the altitude, that number represents what relationship between the lengths of the two hypotenuse segments. If you said geometric mean, you'd be absolutely correct. So this number here, this position here is replaced with the geometric mean, which is the length of the altitude from the right angle. So this is my H1, this is my, well, let me write that down. You see, this is my H2, as you can see here. I'm sorry, H2. This is my H1. So that's what these represent, and these represent my altitude. Well, why is that relationship important? Well, we're going to be setting up a lot of problems involving the geometric mean, so that proportion is very important. Let's take a look at another relationship. Okay, so let's take a look at another relationship. And this relationship involves the fact that triangle ABC is similar to ACD as well as triangles CBD. So it's the main triangle similar to both triangles. And here are the proportionality statements that are a result between both. Do you notice any geometric mean relationships? Well, if you say, well, look, there's an AC here and there's an AC here, well, what does AC represent? Well, AC represents one of the legs of the main triangle. Well, what does AB represent? Well, AB represents the entire hypotenuse. So I have this relationship that can be described based off this relationship, where H represents the hypotenuse, AC represents this leg, AC represents this leg, and AD represents H1, which is the part of the hypotenuse that's adjacent to the leg in question. So that's the relationship that results from that similarity triangle. But what about this similarity triangle relationship? Well, let's take a look. Do you see any geometric mean relationship here? Well, if you said you do see it, you see that you have here BC and CB, which we know CB is the same length as BC. So here's another geometric mean relationship where AB again represents the hypotenuse, but BC or CB represents the other leg of the main triangle. And then BD down here represents the part of the hypotenuse that's adjacent to the leg that we talked about. So this results in our geometric mean leg theorem. And the geometric mean leg theorem looks something like this. And it varies. The only difference between these two is it depends on which leg you're dealing with, which will determine which part of the hypotenuse you're working with. So let's go back to our notes. So in here we have the geometric mean leg theorem, which means here you have the triangle being divided based off into two similar right triangles by the geometric mean, by the altitude. And therefore we have CB over CB, which is this leg, is the geometric mean of the entire hypotenuse and the piece of the hypotenuse that's adjacent to leg CB. So which part is that? Well, if you said that that part was DB, you'd be absolutely correct. And as we pull this aside, this holds. Well, over here we have a different geometric mean relationship. You still have in this, instead of the geometric mean being the length of leg CB, now this is the geometric mean is the length of leg AC. And as you can see here, AC is a leg, and the geometric mean relationship is that this is a geometric mean between the entire hypotenuse, and if you said part AD, you'd be absolutely correct. So here, remember, it's the part that's adjacent to the leg, and that's the geometric mean theorem. And we're going to do activities today that's going to basically you're going to need to know these two relationships and how to set them up.